So I'm going to speak in this presentation a little bit about Cassandra and Kenshoo, mostly issues we had over the years with Cassandra and how we solved them. And then I'm going to speak about how we, hopefully Scylla is going to make our life easier and we'll have more sleeping hours. Okay, so a little bit about me. As you can see, I'm deep into computers. About 6 years ago, I moved from web programming to big data. Today, I'm the big data team leader at Kenshoo. What we do is mainly we do big data DBA, meaning installation, administration, discovery of new technologies, and so on, data flow design. I believe that big data DBA should also be very familiar with the tool he's working and programming and work with clients. That's why we do about 50% of programming. We write ETL, monitoring tools, and administration tools. A little bit about Kenshoo. We're a 10-year-old company based in Tel Aviv, around 500 employees. What we do is we provide software as a service for advertisement management. So we're not actually an advertiser company. We work with advertisement networks such as Google and Facebook. Today, around 10% of all AdWords campaigns are managed by our service. We work with big companies like Walmart and Facebook and eBay. And basically, they have millions of advertisement entities such as ads, keywords, and campaigns. So first of all, we give them tools to help them manage all those entities. Second thing we do is we analyze the behavior of their end user, and we help them to optimize their campaigns. Okay, so like I said, we recently celebrated our 10th birthday. At that time, obviously, big data wasn't very widespread. So most of our application, we have a pair. We do by client charting. Most of our application is a pair of my SQL and Java application, which we duplicate. So each client resides on a pair of these servers. One of the benefits of working like that is if we have issues with performance or a bug of some kind, it will only impact, most of the time, a very small amount of the clients. Obviously, the next step was moving to big data. So today, we're working with Hive, Hadoop, Spark, Impala. And around 5 years ago, we started working with Cassandra. I think the biggest impact for Kenshoo, the biggest change was that we started moving to a multi-tenant cluster-wide configuration. And that means that now if we have issues, all of the clients get affected. So we're much more sensitive when we have to do changes and deploy codes that are related to those technologies. Most of the jobs we do and run on these technologies, it's batch processing, again, analyzing user behavior, creating performance tables so we can optimize our customers' campaigns. Okay, so Cassandra at Kenshoo, we work with DataStack community. We have 5 clusters, 70 nodes. Our biggest cluster is 40 physical nodes. The biggest challengers there is we have 4 terabyte per node compared to 1 terabyte. It means that a lot of the maintenance jobs are very, very heavy, and we have to be very delicate when we run them on that cluster. So what I'm going to focus here is what I like to call the Cassandra Cost. So usually in classic databases, when you do an insert or update operation, you pay for the operation on that moment. If you do an insert in database, in that specific moment, the database will rearrange its pages, change the indexes, and so on. And as you're familiar with Cassandra, Cassandra doesn't do that. It gives you very fast latency because it just pushes all the data into memory and then append it to disk. We actually do pay that cost later on with other background processes such as compact, repair, cleanup, and then remove. And the problem with this approach is two things. First of all, you don't know when you're going to have that impact. All of a sudden, you make a lot of writes, and in 2 o'clock in the morning, big compact going to start running on your cluster, and you'll start having performance degradation. And the second thing is you don't really know what's the real throughput of your cluster. So you can take a brand new cluster, have 100,000 writes a second for 2 hours, and then all of a sudden compaction will kick in and your performance will go down to maybe 20,000. So I'm going to speak a little bit of, like I said, some of the issues we had to solve over the years, and then I'm going to compare it to Scylla and see how it was able to run the same jobs. So I think the first thing about Cassandra, when you really start working with it, you need a really deep, in-depth knowledge. You have to understand mem tables and SS tables and compactions and repair and all of those processes, and really understand what's happening, because a lot of the solutions you're going to have is based on your knowledge. And the reason for that is I think there's a lack of documentation. And when I'm referring to lack of documentation, I'm not speaking about the fact that there isn't documentation about configuration, but rather what's the actual real-world effect on your cluster. I'm going to give an example later of that. Another issue is tuning per application. So again, you might have a great cluster running, which is running, let's say, batch works, and then you have a new application, which is real-time bidding, and then you have to start making a lot of changes and tuning for that specific application. Lots of custom maintenance over the years. For example, when we added the new data centers, we couldn't run full repair, so we had to write our own script to do repair on token regions. I'm sure a lot of people had to do that. We don't repair when we have problem with a specific node. We won't run repair. We only run rebuild, because, like I said, a cluster wouldn't stand a full repair. This is migration from ScyllaDB to LevelDB. By the way, how many people work with LevelDB as not size tiered? Okay, not a lot. I hope most of you know what it is. Basically, we work with the size tier compaction strategy. And what we have in a cluster, we have around 8 hours a day where we have low processing in our application, meaning we can somewhat run some kind of low maintenance and one on the node. And that's what we usually do. We had to run compact because we had a lot of expired keys we wanted to delete. At some point, the node just grew too big, and those 8 hours were not enough to run a full compaction. And the problem was that the node just kept growing because we couldn't run a full compaction and cleanse those expired keys. So the first thing we found was a JMX hack. There's a JMX hack you can tell Cassandra to compact a specific SS table. So it will not really do the full compaction process, but it will clean, run on a specific SS table and clean expired keys. And next on, we discovered about a LevelDB compaction strategy, which really seems to fit our profile. Now, when you convert a Cassandra cluster or a column family to LevelDB, what it will do, it will run something similar to compaction, and it will start splitting. In case you don't know, LevelDB compaction works instead of working with big SS tables, a lot of small SS table files. So it will start splitting the big SS table to small SS table files. And the problem with this is that it's a cluster-wide configuration, meaning that when you convert the cluster, all of the nodes in your cluster start doing this very big, heavy compaction processes. And like I said, we could maybe run compaction on one node for 8 hours. So obviously, this was not an option. Again, there's this undocumented JMX hack we somehow found where you can convert a specific node to LevelDB, and only that node will start running the compaction. So this is what we did. It's probably the longest maintenance jobs we ever did. This is what like our battle board. Each day we would wake up, convert one node, mark it, and move to the next. Each time we had a server of Cassandra restarting. We did a special script that would keep querying each server, what's its current compaction strategy, and make sure to return it back to ScyllaDB in case it resetted. Okay, GC, I'm sure everyone are familiar with GC issues in Cassandra. Lots of GC underload. Usually GC will start hurting the 95 percentile performance. A lot of time we've seen that if one node has issue, maybe corrupted data or some kind of bug, it will actually affect the performance of all the clients. Until this day, we're doing a full rolling restart to all of the cluster just to make sure all the processes are get a clean start. This is a configuration, like I said, talking about documentation and always having to tune up Cassandra. The RPC server type configuration, when you convert it to HSHA, what it actually does is does connection pooling on Cassandra. So this part is documented, but it doesn't tell you it's going to reduce the amount of memory Cassandra used. This is something we had to realize by ourselves, connecting to JConsole, seeing the number of threads, and then looking at the server and the number of network connection, and somehow realize that if you're going to move to connection pooling, it's going to reduce the amount of memory in GC, and actually it did help. I think the problem with GC is a lot of it is black magic. There's a lot of documentation. Some of it relates to Java 7, some Java 8, some Cassandra 1, some Cassandra 2. It takes days to see the effects. So if we have a problem with where we need to restart the cluster every week, actually trying to fix that would be a big headache, because we'll have to make the changes, wait for around 8 days, see if we have any problem with the application, and then realize if the changes help or no. So we would just rather do a full restart every week, and that's it. Okay, this is the last slide talking about issues. Again, every time we add or remove a node, we have to wait 2 days for the cluster to complete all the extra compaction. If we have servers that for some time is gone off, for some reason is gone offline, and we want to remove it, let's say in the evening, we can't do it. We'll just have to stick with that offline server until the next morning when we have that precious 8 hours window where we can remove it. This is a nice trick. If you're still working with Thrift, you can actually disable the Thrift service on a specific node, and it will still be part of the cluster, still get writes, but it will not actually accept client connection. So you kind of can run some of the maintenance on it and not get too much bad effect to your latency. Again, we can run full cleanup. I think we haven't run cleanup for over a year in a cluster, even though we added and removed a lot of nodes. And again, there's all this stuff in Cassandra. You keep tuning params, such as compaction throughput. So if your cluster has bad performance, you lower the compaction. If you wanted to complete some kind of jobs and you have to do it fast, you'll increase it. Again, there are a lot of recommendations for different versions, so you don't really know what's the best to pick. Okay, so obviously we wanted to evaluate Scylla. The first thing I think with Scylla is we evaluated Scylla as a company, the people that work. We read some of the blogs, looked some of their benchmarks. I think this is a very nice example. I talked a lot about how you need to, in Cassandra, always keep doing fine-tuning. So this is a nice feature. They have it in the blog, the one Dor referred to. This is their disk IO scheduler. So if you have several IO requests, one for compact, one for repair, and let's say one for read, they will automatically give different priority to each of these IO, and obviously they will give the higher priority to read, meaning you'll get the best performance in read. And let's say over time your compaction queue gets larger, they will start giving higher priority to your compaction. So again, this is supposed to save you a lot of tuning and configuration. So the next thing we did is we actually ran a few benchmarks. As you can see, we ran it on AWS. Now this is important to note. In Cassandra, we took DataStax AMI. So the default compaction throughput is only 16 mega. And this is a very strong server. I think it has like 6 or 8 SSD. So again, unless you're familiar with this stuff and you have a lot of experience, the default user is just going to take it and have very bad performance with Cassandra. So we did the following changes. In Scylla, we just took it out of the box. So the first thing we evaluated at Scylla was the GC. Obviously, we didn't have a lot to do since Scylla is written natively in C++. There is no garbage collection, and that's one of the things I told the guys at Scylla. Give me the same Cassandra, same benchmark, no GC. It's good enough for me. Okay, so moving on to repair, you can see the setup. We took a 3-node cluster, deleted all the data from one node, and then ran repair on that node. You can see Scylla did it a little bit over 11 minutes, which is 2.5 times faster from Cassandra. And next thing is cleanup. Like I said, we have issues with cleanup, and it's an important point. We took 270 giga of data, 4 nodes cluster. We decommissioned one node, so obviously the other 3 had more data. Then we join that node back to the cluster, meaning the other 3 has extra data we should clean. This is very impressive. As you can see, Scylla did it in less than cleaning from 370 gigabyte to 270 gigabyte. This is in seconds, so less than 4 minutes, almost 9 times as fast. So if we had this configuration in our cluster, that would be amazing. We could have probably ran a full compact in less than 2 hours. This is pretty good. Next thing is compact. We run stress for 30 minutes. As you can see, again, pretty much amazing. Scylla ran compact in 200 gigabyte, reduced to 72 in less than 2 minutes. It took Cassandra 15 minutes. So again, speaking about the cost of Cassandra, you can see that in Cassandra, after running a stress for 30 minutes, you still have to pay 15 minutes of compaction. And in Scylla, the cost is almost not there. It's only 2 minutes. Latency and throughput. So why actually do we care about latency if we're doing mostly batch? The reason is we have hundreds of different applications running millions of requests. And those applications are preparing reports for our customers. So even if we have a small jump from 5 milliseconds to 7 milliseconds, it means that some reports are not going to be there ready for our clients. It's 9 o'clock in the morning. And sometimes when we did have the issue, it did happen, and some of our clients didn't get their reports on time. So as you can see, one thing to note is our values is 1.5 kilobytes. So they're a little bit bigger than most of the benchmark you'll see. So the numbers of IOs per operation per second is a little bit lower than what you used to. We took a mixed configuration of 3 writes and 2 for every 2 IO read, which is average to what we have in our cluster. So it started with something pretty low, as you can see. Sorry. All right. 2,000 operation per second. This is the write operation. This is the read. You have here the read mean, median, 95% L99, and the same for write. You can see at this point 2,000 operation per second. This is a 3 nodes cluster. Cassandra is pretty good, even in the 99 percentile. Scylla is always below 1 millisecond. Jumping to 4,000 operation. You see that Cassandra is starting to have some stress. The 99 percentile is, is a bit high, but still it's pretty good. And 8,000 operation, you start seeing the degradation in performance. You see that even the 95 percentile is Cassandra is beginning to be a little bit higher. And 12 operation, again, Scylla is very stable at no more than 1.5 milliseconds, but the 99 percentile is already pretty high. So probably if you have some kind of real-time application, you're going to see the effects. This is 16,000. At this point, you see Cassandra just doesn't give any good results. Even I think for batch operation and stuff, it's very bad results. It probably wouldn't work good. Scylla is still amazing at 2 milliseconds, even in the 99 percentile, much better than Cassandra. And at this point, this is the best Cassandra could have given us. We couldn't get more operation from Cassandra, but we want to still keep testing Scylla and see what we could get out of it. So again, this is 20,000. You can see below 2 milliseconds, even for the 99 percentile. And 40,000 operation, less than 3 milliseconds for the 99 percentile. Now this is pretty impressive. Our cluster, which is 40 physical nodes of Cassandra, we maybe have some burst for a few minutes of 30,000 operations. So this is 40,000 operation in a 3-node cluster. We didn't continue testing after that. The latency started to get higher, and these were pretty impressive results, so we didn't need to do any more benchmarks. Our conclusion at this point is obviously all the stuff I talk about, compaction, repair, cleanup, are much faster in Scylla. The consistency in Scylla is much more higher under higher load. Moving forward, we are starting to integrate Scylla in one of our inner production monitoring system. That's it. If you have any questions.